here. Somehow, when Jess contacted me about giving a plenary talk, I missed the first line of the theme for this year with the movie reference, and so I don't have my red beanie. But I did latch onto the second part, which is science, management, and connectivity. And I'm going to try to talk about that a little bit today in the context of thinking that we've been doing about recreational fishery landscapes. And basically my goal today is to share some of the ways that we've been thinking about these systems, and hopefully some of that's at least a little bit useful or thought-provoking for you. Okay, so to start with, what is a recreational fishery landscape? Here's one. This is the landscape in northern Wisconsin on the border with the Upper Peninsula of Michigan, where I do a lot of work. And you can see there are a bunch of lakes, right? So there's a bunch of fishing opportunities in the landscape. Excuse me. So your fishery landscape might be a little bit different from this. Where I live in the Hudson Valley, fishery landscapes might have lakes, small streams feeding into the Hudson River itself, trout streams in the Catskills. You know, it looks different from this landscape, but I think a theme in any recreational fisheries landscape is that there are a lot of different places you can go fishing, spread out across some amount of space. There are fish in those places. Here we've got more fish in some of the lakes, less fish in the other lakes. In this case, they're all bluefish, but probably there are different species there besides bluefish in some of these lakes, right? So we've got different fishing opportunities available. We've got people, we've got anglers who are really efficient predators moving around that landscape and doing something like optimal foraging, right? They're looking for the best places to kind of meet their goals of fishing. And by doing that movement around the landscape, they're linking those different patches or those different ecosystems together. And then finally, we have institutions that are involved in the management of these systems. So those institutions might be big formal places, with big pillars out front like the DEC, right? They might be much smaller institutions like a town or county government that sets land use regulations or lakeshore regulations. They might be a nonprofit organization like Trout Unlimited or something like that, or a lake association, which, at least in my landscape in northern Wisconsin, are often pretty involved in fisheries management. They also might be like lowercase I institutions, right? So things like a catch and release norm, sort of an agreed upon or sort of informally agreed upon cultural institution, right? So social scientists talk about institutions ranging from this like really formal big columns out front to much more informal kind of rules of use institutions. All of those things are potentially involved in kind of dictating how the dynamics of these systems work. Okay, so those are recreational fishery landscapes, or at least that's what I mean by recreational fishery landscape. I'm going to assert for a few minutes here that those things are potentially vulnerable, okay? They're vulnerable to stuff like climate change, species invasions, and I'll kind of hit at a couple examples of that through the talk today. Probably most of what I'm going to talk about is vulnerability to overfishing. And I think we actually don't have really great data that demonstrates that recreational fisheries, inland recreational fisheries, are vulnerable to overfishing. I'm not sure that means that they're not. I think it means that the data are hard to get. For a moment, in place of data, I'm just going to assert with an anecdote, which, as we all know, is excellent scientific practice. Here's a couple people on our field crew on one of these lakes on the Wisconsin-Michigan border where we work. These are really low connectivity lakes, so angling is sometimes our most efficient way of capturing fish. We do a lot of fishing up there. A set of the lakes that we work on are private. They're on a big university research preserve. There's no public access. And the fishing is great. Like, most of the time, if you go 2 casts and don't hook anything, the other people in the boat start looking at you funny, right? Like, the fishing is really very good, especially when you compare it to stepping a mile away off of that private reserve, essentially, into public lakes, where you go a lot more casts without catching any fish, right? So there's a little bit of anecdote that suggests that, okay, when there is public access to a fishery, maybe it doesn't collapse the fishery, but at the very least it drives catch rates downwards, right? And you may have examples of that from your own fishing in more remote and less remote places, things like that. Here's at least a little bit of data that sort of shows the same thing. This is from a great and very influential paper by John Post and colleagues in 2002. This is the invisible collapse paper. And here's a little data suggesting that, or showing the catch per unit effort is much lower in a set of lakes that are a short travel distance away from Vancouver, British Columbia, so this is within a few hours drive, than in lakes that are further away, right? So essentially, as that effort sort of decays as you move away from the population center, the fisheries are in better shape, or at least there's more fish there to be caught. And that paper in particular, I think, and some other things that happened around that time, spurred a bunch of work, often modeling work, sometimes linked to data pretty strongly, sometimes linked to data a little bit less, but sort of demonstrating the possibility, at least, that high levels of recreational fishing effort could really cause collapses or something like collapses in recreational fisheries. So here's an example. This is from Len Hunt and colleagues in the area around Thunder Bay, Ontario, and these are walleye fisheries, if I remember correctly. And the colors here, which look miserable on the screen, red is collapsed, which is something like under 10% of unfished biomass or something like that. Overexploited, which is, I don't know, less than 50% unfished biomass or something. And then essentially not exploited, so very close to unfished biomass. And you can see that under a fairly reasonable set of assumptions about some of the model parameters, you get this pattern of collapsed fisheries close to a population center, sort of okay fisheries further away, and then you have to get pretty remote before you see these fisheries that are really in great shape. Okay, so that was all about the ways that high fishing effort may potentially degrade catch rates or fish biomass to a level where we would call them overfished. Of course, catch rates or fish biomass are not the only things we care about in fisheries. Fisheries, recreational fisheries, are recreational, and so a lot of what we care about is the satisfaction of people who are out there doing the fishing, right? And the fishing experience involves not just catching fish. If it involved only catching fish, I probably wouldn't go fishing because I don't do much of that. It also involves other aspects like the possibility of hooking the fish, the availability of hookable fish, right, which can be decreased by excessive effort. For some people, it includes things like solitude, right? It may include limited sort of physical access to available fishing spots, as in this picture. So there are all these other aspects of the fishing experience that are also potentially vulnerable to very high effort. Okay, so that's a little bit of background, and what I'm going to do for the next few minutes here is talk about what we see and some other kind of themes in the literature about what are some of the challenges that make these fishery landscapes potentially vulnerable. What are some of the complexities that mean that they're hard to manage with, okay? And I'll walk through this kind of trying to hit some themes and then give a few examples in some cases of ways in which we see this. I think one of the challenges involved in managing these systems is scale. So this is a map of Vilas County, Wisconsin. Here's the UP of Michigan right here, not shown. This is the landscape that I do a lot of work in. And there's over 1,000 lakes in this county. You can see the scale bar there. There's 10 kilometers. It's not a huge place. There's an awful lot of water. And so as a management agency, you're sort of stuck with the problem of, wow, there's this huge number and huge diversity of, to some extent, individually operating sort of distinct fishery ecosystems all out there, right? It's an impossible problem to try to have the data to really understand and manage each one of these. You could imagine sort of a counterfactual where, okay, well, what if we turned over the management authority of those systems to town governments or local lake associations or something like that, right? So they're right there at their own lake, they know the system well, they can set the regulations for that lake to manage that lake well. But there's kind of a scale problem there too, because of course the dynamics of that fishery are intimately connected to the fisheries around it because the anglers can move around, right? And so sort of devolving the power to that local scale doesn't really work either because of this kind of network effect of the humans connecting all these things together. There's also a time scale problem, I think, in managing recreational fisheries. This is a great picture and a story I really like from that invisible collapse paper by John Post. And the gist here basically is, this photo was taken in the 40s. The girl here, they're holding up a string of a walleye. The girl here would later grow up to become the mom of one of the people who's a co-author on this paper, okay? The family's holding up a string of a walleye at this lake in Saskatchewan maybe, where they ran a guide service for many generations. In her grandmother's time, that guide service was focused on lake trout. But by the time the girl was growing up, the lake trout fishery had collapsed. That was okay because the family switched over to guiding for walleye and had a very successful guiding business guiding for walleye, right? They did very well with walleye. By the time the little girl's kid grew up and was having kids of his own, and is an author on this paper, the walleye fishery had collapsed. That was okay. They had switched to northern pike instead. The family was now kind of leading guides on northern pike. But actually, as he was growing up, as his kid was starting to grow up, they were starting to see signs of evidence that the northern pike fishery was going to collapse, right? And so, you know, that's, I think I said like 4 or 5 generations there, right, over which you see this sort of serial collapse of multiple fisheries in the same place and start to think, well, okay, we really have a problem, right? So that kind of generations-long time scale, I think, is a real challenge for any of us in understanding any problem, and it's a challenge for us in managing fisheries as well. Excuse me. One of the challenges we face is that anglers have really different goals and values. So this is sort of cartoon data, but modeled after real data from a nice paper by Fiona Johnson and her colleagues. And it's showing for some sort of cartoon versions of kinds of anglers, so generic anglers, consumptive anglers, or trophy anglers, the extent to which they either prefer or tolerate certain things. Like the white arrow here says trophy anglers have a strong preference for fishing as opposed to doing anything else in their life, right? Whereas generic anglers, meh, you know, they'll go fishing, but they just as soon sit and watch the ball game or whatever else instead, right? Different kinds of anglers will tolerate crowding more or less, right? And so we know that there's a lot of different ways that people approach fishing, and that means that we're managing not for just one kind of thing, we're managing for a lot of different kinds of things. That doesn't even get into the fact that there are other goals and values that are involved in managing these aquatic ecosystems as well, right? So here's a landowner whose goals and values for their property involve a big lawn that they fertilize and put some pesticides on and some riprap control so that they have a nice stable shoreline. Those things may or may not be consistent with some of the goals that anglers might have in fishing on that same water, right? So we're dealing with a lot of different demands on our resource. This, I think, is a really big one. Fisheries, at least in most parts of North America, are a common pool resource, right? That means that just like the village green in your village that you live in, anybody can go graze their cows there. I always have an incentive to graze one more cow there because that means I get to produce a little more butter or whatever. But if every one of us grazes one more cow there, or 2 more cows there, or 3 more cows there, then we degrade the resource, right? It's a finite resource that can be degraded, and the incentives of the users aren't really matched up well with that, the fact that the resource is degraded, right? Fisheries in North America operate that way. That's sort of one of our fundamental challenges, I think, in managing the recreational fisheries, like other complex systems, have lots of feedback dynamics that can produce unexpected outcomes and that can be difficult to understand, difficult to work with. One good example, I think, is the feedback between fish abundance and catch rates. So here's the typical catch equation, catch equals QEB, right? And just rearrange so that we have catch per unit effort, so C over E, as a function of biomass. Our typical catch equation says, okay, well there's a constant proportionality between those things, right? There's a straight line relationship between catch per unit effort and biomass. The slope of that straight line is governed by Q, the catchability. That's a really great feedback in trying to manage one of these big connected systems, because what it means is that if you've got anglers on one of those lakes I showed a picture of, and they start to fish down the biomass in that lake, eventually they get to the point where catch rates are low enough that, if they value catch rates at all, they say, well, this sucks, I'm going somewhere else where the catch rates are better, right? And so there's this sort of self-control mechanism of moving effort away from places where biomass is being drawn down, maybe letting the biomass recover there, and shifting the effort somewhere else for a little while. The problem with that, we know, is that that constant of proportionality, the catchability coefficient, actually isn't constant in a lot of cases, and there's great evidence about that in marine fisheries. There's now really pretty good evidence about it in inland recreational fisheries as well. Here's a study from Hillary Ward in, I think, rainbow trout lakes in British Columbia. And in this set of lakes, you can see there's a nonlinear relationship between CPUE, angler CPUE, and fish density, and that occurs because of effort sorting. So basically in the lakes where the abundance is lower, we can have a little pool going on. How many more times I do that during this talk? In lakes where the abundance is lower, the fish are harder to catch. The idiots who can actually catch fish like me don't go there. It's not worth their time. Instead, the really expert anglers who are very good at catching fish go there, and they still manage to maintain relatively good catch rates going, right? Your regular idiot angler like me goes to the places where the fish are really abundant and they're easy to catch, okay? So effort sorting can produce this sort of nonlinear relationship between catch rates and biomass. We also know that fish aggregation can do the same thing. These data are from a really nice study by Colin Dasso, where we had a lake and we intentionally drew down the biomass of largemouth bass in that lake over time. So we were repeatedly electrofishing. That meant that we had repeated population estimates, and every time we did one of those rounds of electrofishing and estimating the population, we would take a bunch of fish out and move them over to another side of the lake, basically. It's one of those lakes that comes to kind of a constriction point. We had it divided in half with a curtain, and so we just dumped the fish over into the holding pen, basically. While all that's going on over the course of a year, we had a crew of anglers who were repeatedly, the same crew of anglers, same people all the time, who went out regularly and angled on that lake. And so what we see is that even in the absence of that effort sorting mechanism, these are the same anglers all the time, we get, you can run the biomass of the population down fairly low before you really start seeing a noticeable decrease in the catch rates, right? And so what all that means is that you have, either because of effort sorting or because of mechanisms like aggregation, the fish go to sort of preferred habitats, and they all crowd into those preferred habitats. You get something more like this. As the biomass goes down, the anglers stay happy and stay happy and stay happy until basically you've gotten to the point where the biomass is collapsed and the catch rates finally collapse. Okay, another challenge of recreational fishery landscapes is that they have slow drivers. And this is not your grandmother or your grandfather or your parents or you even. This is things that have a big effect on the system and that move slowly. So here's an example focused on climate. This is the probability of successful walleye recruitment or high abundance of largemouth bass. Fit to some data, basically it's a model fit to some data by Gretchen Hansen and her colleagues. And you can see that as you warm up the climate, you approach this sort of threshold point where the likelihood of having successful walleye recruitment tanks and the likelihood of having a bunch of largemouth bass goes way up, right? So climate's kind of a classic slow driver. You know, it takes years and years and decades for changes to really manifest. Again, that's a hard problem for humans to wrap their heads around, but those things have big effects on these systems. I think a lot of the slow drivers that we think about are illogical. We got interested recently in thinking about slow social drivers of change in fisheries as well. So Chelsea Neiman and I took a fairly standard bioeconomic model of a recreational fishery and noticed that there are a few sort of social processes in that set of mechanisms that control the rate at which fish are removed from the system, okay? So the black line here is the growth rate of fish as a function of biomass. The red lines, I don't know if you can see the colors at all, the dashed lines are different scenarios of the removal rate, the function that relates catch removals to biomass. And basically, there are several kinds of slow social change that, as that change happens, you essentially shift that removal curve up like this. You rotate it up. And that means that the equilibrium point, the point where the removal curve and the growth curve cross, which determines the equilibrium biomass, starts shifting to the left. It shifts to lower and lower biomass, okay? So here's a model of an open access recreational fishery where as social change happens, you're sort of slowly degrading what you thought was an equilibrium. The equilibrium of biomass or abundance of fish is sort of slowly decreasing through time. So what we did is to look at, okay, well, what are those social mechanisms, and is there any evidence, like is there any reason you would think that maybe that kind of social change actually happens? One of those mechanisms, in the model is decreasing marginal cost of fishing effort, okay? So if over time it gets cheaper, that one more day of fishing by an angler out there becomes cheaper through time, then that can drive this kind of change that I just talked about. What might make that happen? Well, one of the big costs that anglers incur in going fishing is travel time. Most bioeconomic models of fishing effort, travel time is one of the major factors. And so we looked at this landscape in northern Wisconsin and pulled out some data on road density, which if you look over the course of 60 years, has been slowly going up and up and up. And really this was inspired, maybe the whole paper was to some extent inspired by the fact that this is a place that I've been going for, I don't know, 20 or 25 years or something like that. And it's hard to get to. It's kind of far away from a lot of things. But it's a major vacation destination because there are a lot of lakes and people go fishing there. And over the time that I've gone there, the roads keep getting wider. Like the highways have more lanes. It's a little faster. It's a little easier to get there. The roads around the county, they're, the dirt roads turn into paved roads. And so if you have decades-long perspective, you see that, yeah, okay, maybe it's a little easier. Maybe my travel time to get to any of these places is very slowly going down through time. Another mechanism that can create this kind of change is increasing catchability. Here's an example of increasing catchability through time. This is, I don't know, a couple decades or something like that. This example is from a marine commercial fishery. There is, I think, no great data really clearly demonstrating increases in catchability in a recreational fishery through time. If you're a student, you should find a way to do that. It would be a great service to the community. It would be famous and rich forever, probably. Despite the fact that we don't have great evidence for this in inland recreational fisheries, it almost certainly happens. Technological change, the advance of sonar, changes in technique, changes in gears, all of those things tend to increase catchability through time, and we see strong evidence of that in lots of marine fisheries. It almost certainly happens in recreational fisheries as well. And then the last mechanism that we looked at is catch importance. So anglers value catching fish. They value other stuff like solitude or time with friends or time in nature or whatever. And if the importance of catch in how an angler decides to go fishing decreases relative to the importance of those other things, then that can also drive this kind of slow social change that degrades the equilibrium biomass. The only data we could find that even came close to talking about that was, this is again, I think, a fishery in British Columbia where they surveyed anglers over, I can't even read that, 15 years maybe. The green line here is non-catch motivations. The purple line is catch motivations. It turns out there's not a significant decrease in this, and there's a stronger and significant decrease in the catch motivations. And so maybe that's evidence that that kind of thing happens. We suspect that it actually happens more than the data would suggest. If you think of your own fishing experiences, I think this, especially on sort of a generational time scale, right? Like fishing is a thing you do, it's a thing you pass on to your children. Your child doesn't know that your grandparents used to catch 10 bluegill a day in this lake. They grew up thinking that 5 bluegill a day in this lake was a great day, right? And so they value the effort, they value the going out to fish. The catch, the expectation of catch degrades, and I think that's probably a mechanism that occurs in real life. These systems have surprises. I'm not going to say much about this one except that here's an invasive species. It came in, it became more abundant. Some fish became less abundant. Surprises happen all the time in recreational fisheries and in lots of other complex systems, and they make the systems challenging to manage. Okay, so I'm going to try to wrap up this part of the talk. Jess, how am I done, by the way?
10 minutes.
Holy crap. Okay. And I'm going to talk fast for a little bit here. Why these systems are difficult to govern. There's a lot of different systems. They have complex dynamics. They're linked by human decisions that are made with imperfect information. Agencies have to deal with this with limited budgets. And people, because of the open access issue, don't face the full costs or benefits of their actions. So these are complex social ecological systems. They have open access to a common resource. They're difficult to manage. This is a rainbow and some kittens. I just felt like things had gotten a little grim. Okay, but it's a nice transition because now we can talk about what we do about that. What are some of the opportunities? And I'm going to talk about some things I think we can do or change, or that are at least worth thinking about a little bit, about how we manage these kinds of landscapes. A lot of my thinking here is pretty heavily influenced by a great paper led by Robert Arlinghouse in PNAS a few years back. Definitely worth reading. A really great book by Wency Biggs, edited by Wency Biggs and her co-authors, about building resilience in social ecological systems. If you haven't looked at either of these things, go do it. Some of the examples I'm going to talk about are lifted directly from these places. Others are at least heavily influenced by. And I'm going to, as I go through these, I'm going to go from stuff that I think basically we're already doing or isn't maybe much of a lift to stuff that's a little bit more out there. We need to measure success appropriately. Recreational fisheries are recreational. They're about angler satisfaction. Our goal should not be things like MSY. It should be more about number and quality of fishing opportunities and angler satisfaction. Maybe it's a little more complicated in mixed fisheries that have commercial and recreational uses, but this is the way we should be thinking about them. I think, by and large, we probably do that mostly these days. We should maintain a diverse portfolio of fishing opportunities, in part because anglers are diverse and we're trying to make them happy. So we want fishing opportunities for the people who want to paddle in for days and have some solitude and be able to fish in a lake that doesn't get fished very much. We want fishing opportunities for people who don't want that and instead want a boat launch and some great fishery they can access out of that boat launch. My sense is that we do this to some extent, and in fact I don't know anything about the development of New York State, the new New York State Trout Management Plan and the change in regulations that happened a few years back. It seems to me that that kind of thinking was probably part of what went into developing this, and I bet some of you in this room know more about that than I do, maybe all of you. So diverse portfolios are great for satisfying diverse anglers. They also hedge against change. We talked about some of those slow changes or surprising changes, things like climate changing the relative abundance of species, or invasive species changing which species do well. If we have a diverse portfolio of kinds of fish we can fish for, we hedge against some of that change, just like in your retirement account you hedge against change, right? Another really important reason, I think, to maintain a diverse portfolio that I think is a little more out there is that it may help to counteract this idea of shifting baselines, right? So I said the thing about, okay, you become used to the fact that you grew up with 5 bluegill being the norm for this particular lake, and that norm just kind of degrades through time. The more places we have in the landscape where somebody can go, even just occasionally, once a year, once every 5 years, and see, oh wow, this is what bluegill fishery could look like. Oh wow, this is what a lake trout fishery could look like. I think that helps to counteract that shifting baselines problem, right? It helps people to realize the extent to which most of the fisheries they access are managed at a lower abundance than they might be. It helps people to think about the trade-offs that are involved. We should collect the right data. We collect a lot of data. It's hard to do. I think we could do more to try to deal with the fact that these are big landscapes with lots of fishing opportunities, and we need to think about how to collect data at those scales. So here's an example from Ashley Trudeau, who went to this county in northern Wisconsin and did some work with sort of traditional creel surveys, which are very intensive on a few lakes at a time, and those lakes kind of rotate. So every 5 or 10 years, the DNR, the Natural Resources Agency in the state, rotates through a small set of lakes where they kind of do a great job of estimating effort and catch and things like that. Actually instead said, okay, well, let's kind of blitz this. Like, let's hit a bunch of lakes with a random design where we go out for like a 4-hour session and we might hit the lake 2 or 3 times over the course of the year, but we do it on a whole ton of lakes. And maybe let's combine that with some aerial surveys where we can see 100 lakes in a day. And then let's use some statistical models to try to separate out, okay, well, can we estimate effort across a much larger set of lakes if we do that? And the answer is basically yes. It's got some strengths and weaknesses. But I think that's the kind of scale we often need to be thinking about in order to manage these really big connected landscapes. Chelsea Neiman put together a nice paper thinking about the kinds of data we can get out of creel surveys. And I'll just say here that, I don't know if you can see the colors again, but the black text is stuff we tend to do in creel surveys. The red stuff is stuff that we maybe could do more of. And so there's some opportunities, particularly kind of on the social side or the kind of social ecological interactions, where by asking different questions, we can get a lot more information about the decisions that anglers are making. And because the anglers are the predators and they're the ones that are linking all these systems together, that's really key information. I'm going to skip over that for time, even though it's really cool. We need to be collecting the right kinds of data. More broadly than that, I think we need to be encouraging learning. Social ecological systems are complex, they evolve, and so our understanding of them is always incomplete. And so we need to approach them sort of in the spirit of learning about them all the time. And I think that means things like adaptive management, it means things like management experiments, and it means communicating some of that to the public to say, like, we don't have all the answers, we're learning, let's learn about this together. I don't think we do this. I think we can think about, I'm sort of getting into the more out there stuff, right? I don't know whether we can actually do this, but it's really, it would be cool. It might be really powerful. I think it's worth thinking about. Some of these slow variables and feedbacks, I wonder if we can manage. So, for instance, I talked about decreasing cost of effort being a thing that maybe degrades equilibrium biomass in fisheries. I wonder if we could counteract that, you know? I wonder if we could make it a little harder to access some of the places where we go fishing, or at least resist the urge to improve access everywhere, right? Or can we be more careful with the regulations we use about gears to counteract the tendency for catchability to increase through time, right? So I think thinking about ways that as managers we can influence some of these slowly moving but important variables is really important. We could give anglers more power. This is a really neat study in German fisheries that are managed by fishing clubs. The fishing club has rights to the fishery. And this is, again, Robert Arlinghouse's group. Maria Fujitani was the lead author here. And they did an experiment where they had a bunch of these fishing clubs. Some of them they gave a lecture to about sort of principles of stocking and other ways of managing a lake fishery. Other groups, randomly assigned groups, they had participate in sort of adaptive management of the decision-making about the management of that fishery. And what they found is that the groups that were participating in the adaptive management, if you think about the way that people make decisions here in this cognitive hierarchy, those groups actually had significant changes in their beliefs, their attitudes, their norms,